Placing rooms in a dungeon is easy, but deciding which ones connect and how, that is where things get tricky. Out of all these rooms, how should we decide which ones are connected? And what if some of them can only appear at a certain time? I have run into this over and over again as I was making my own dungeon generator. And after a long research and experiments, I have finally found my answer. By the end of this video, you will understand the hidden rules behind corridor generation. And as a bonus, I'll also show you how to code it in Godot. Okay, so look, connecting corridors is pretty complicated actually. Well, there are many ways to do it. There's one notable way to do it, but we're going to talk about why we want to do it that way or we don't have to do it that way instead of just spouting out all the algorithms and potential solutions that may solve this problem for us. So ideas are simple, I think. We have some rooms that we placed. Out of all these rooms, how do we decide which of these rooms need to connect? There is no point in trying to connect rooms from here to here, right? Because ideally, you have this dungeon where a bunch of connections are happening within the space. As soon as you choose these two connections that are far away from each other, you have this scenario, right? Basically, we decided that connections needs to be neighboring. The rooms that are connected should be considered neighbors. How do we decide programmatically that two or some rooms are neighboring each other? The greedy algorithm would be, my initial instinct might say, well, when I'm thinking about this one, and I say, I want to connect it to some of these rooms, and I want to only connect it to neighboring rooms, I may say, well, I'm going to go through each of these connections and figure out how long the distance is, and then choose the two shortest. It may work, but only problem is that you're going to have to do that for every single room. Now you decided, okay, these two are the connections, and then you get rid of all this, and now you go to the next room, and then you consider, okay, well, which ones are my neighbors, and then it goes through every single neighbor and chooses the two closest one, and then so on and so forth. Is there a better way to do this? I'm not sure. But what we do have is something called Delaunay's Triangulation. Delaunay? How to pronounce Delaunay Triangulation? I don't know. It's Delaunay for me. So I'm going to call it Delaunay's Triangulation. Okay, quick interruption from future Ezra here. I wanted a quick word from our very special sponsor today, and it's me. I'm the sponsor. So I've been getting a ton of DMs and comments of you guys telling me that you love my teaching style. And, it makes me feel good because I always try to go deep on the why, like how computers work, what data structures to use, and what all these fundamentals mean. Because as you know, I want you guys to have a long-lasting knowledge that is not just simply a copy and paste. But here's a real reason why I decided to make this sponsored section. I'm running into a bit of a wall here, and I need your help. So as you can imagine, there is a bit of a limit here on YouTube because we're trying to make something that is fast and entertaining for the algorithm. So I end up cutting a lot of the deep dives, and I can't really do all the fundamental building block building in all of my videos. And that is why I created this 30-day beginner Godot starter course. And the goal is simple. I just want you to make your first game in 30 days. And we don't just go over how to use the game engine. We cover fundamental coding concepts and building blocks so you can eventually stop watching tutorials and start making your own dream game. And here's the best part. The course comes with a private Discord community and a weekly call with me. And there we can talk about your specific projects that you want to create and the lessons and everything else that gets you stuck. I am listing this course at a fair price of $97, but if you join right now, you get 50% off with the code Godot1. And look, this is the absolute best way to support me so that I can continue making free content here. I'm going to pay close attention to course students to make sure everybody gets the absolute best value out of it. So if you're ready to get serious, check out the link below. Okay, that's it from me. Let's get back to the video. So let's assume that we have 3 points here, P1, P2, and P3, right? If you draw a circle such that the points are on the outer line of the circle, like on the circle, if there are no other points inside of the circle, if you can draw a circle with 3 points where there are no other points within that circle, then these 3 points are considered neighbors. Okay, well, this is like really complicated mathematic way of saying basically, hey, if I drew a circle around 3 dots or 3 locations, if it has more dots inside, that means we got to change it. Or for example, we do this, there's a point in there. So that means this is not very Delaunay. This is not a Delaunay triangulation because there is a point here. So then we'll have to go, okay, well, this is not real. They're clearly not the type of neighboring we want to create. Let's redraw this. So we're going to say, well, instead of doing this, I'm going to flip one of the points to this. And then I'm going to try to draw a circle. Or if I can do that, that'll be great. Something like this, right? And then go, oh, yay. Now this is a neighbor. So I go, check. This is locked in. They're neighbors. And then now we have to go, okay, well, this one, let's choose 3 points. And then if I draw a circle around these, so if I say, okay, well, these 3 points now, we're going to draw something like that. So anyways, you go so on and so forth. So what is the algorithm for figuring this out? I think that's the question here, but we're going to get back to that. We just have defined what quote unquote neighboring is. So in my brute force algorithm, I said, well, maybe neighboring means that the 3 points are closest to each other against other people, against other rooms. That definition might work for your dungeon, and you're okay with going through this like algorithm of brute forcing everything because it's just in a square. And if you only have like 10 rooms at most per dungeon, then that's like the easiest way to implement it. So maybe that's what we're going to do. But what's popular, what a lot of people use, I don't know why, but they use the Delaunay's triangulation to first determine what the neighbor is. So what's the point of doing this? Why are we even deciding what the neighboring dots are? By finding the neighboring connections. So for example, we have something like this, right? Each of these edges are potential candidates. So we're not saying we're going to connect all of these things, just like we said in the beginning. Some of these can be used, some of these lines can be kept to create a believable connection that will create a dungeon. So that's why we use Delaunay's. I swear I said that name differently every time I said it today, but you get the point. My other suggestion was just brute forcing it and finding the 3 to 4 closest connections or whatever. I mean, you can think about your own ways to do this. It doesn't really matter. Figure out the neighbor somehow, and that'll give us a potential connections. So now we have the neighboring connections. We can't use all the connections, right? Well, maybe some dungeons can, but we don't want to. How do we trim it down? Instead of figuring out how many can we get rid of to make it look like a dungeon, we can start from the least number of connections we can have to have a believable dungeon first. So how do we make it so that there are basically least amount of connections so that every single room is connected? So let's say I start from 1 and I say, okay, well, 1 has been visited and it's part of the map. So we say, well, node in map, 1 is included. We've already gone there. Map is able to get to the 1 because it's starting point. And we say, well, what are neighboring our already existing nodes? And we have 2, 3, and 4 as potentially a candidate. Instead of looking at our nodes as a potential, we're looking at the edges, the connection, because that's what we're trying to figure out. So let's say we have connection A, connection B, and connection C. Candidate, this is an N, by the way. Candidates are A, B, and C, right? Do any of these connections go to the node that we haven't already visited, right? And in this case, we just started. So, let's say this is node 2, 3, and 4 here. So A, B, and C are all potentially a good option as we're making this map. Which one of these edges or connections do we choose first, right? There are several ways to do it. One, we could just choose randomly if we don't care about how the dungeons are created or how the dungeons are formed. But if you say, well, I want my dungeon so that each of the connections are shortest connections possible, then out of all the candidates, we can make it automatically sort and choose the shortest one. So in this case, B is the shortest one. So we could say, oh, I'm going to choose B here, which means we're now visiting node 3, for example. Nothing stopping you from using the longest connection or random connection, or maybe you do shortest for 50% of the time and longest for the 50% of the time. It doesn't really matter. But to be consistent algorithmically, we can choose the shortest connection for now. And reason I do that is because that's a type of graph. Minimum spanning tree is formed this way. But for me personally, for my dungeon, I don't need it to be the shortest thing. Like, that doesn't guarantee anything for me. So actually, I would probably go for something random here, like choose random edges. But basically, that's the idea. So let's say we choose B. So B is strike out. So we have edges in the map. We have B. And then node 3 has been visited, right? Now we say, well, this is no longer a case. Let's look at what other connections we have. So we have this, which is, see, D, E, F, and then that connects to 5 and 6, right? And now we have to go, oh, all right, well, now we have new connections D, E, and F, right? 1, 2, 3, 4, 5 options, right? And then once again, we can choose the shortest one, random one. Once again, I'm going to just choose a random one. Let's say I choose D here and strike this out. Now we have D used. So we include D. So we have this. And then now we're visiting node 2. Well, interesting is happening as I do this, right? Some of these candidates now are connecting the 2 nodes that are already visited. So it's kind of useless. So we can get rid of this. A is no longer an option. And so you keep going, so on and so forth. You keep considering new edges. You keep considering new edges and select one of those edges. And eventually you get something, I think, like this, let's say. Eventually you get to a point where every room is reachable and there are minimum number of lines required in order to connect them, right? Look, 1, 2, 3, 4, 5, 6, 7, 8. 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So we have 13 rooms. And then in order to connect 13 rooms, you need 12 lines, one less than the room number. This detail doesn't really matter, but I'm just saying this is good and all. Like if I'm starting here or if I'm starting here, this is an interesting dungeon. Let's think about as a player's perspective. Like if I start in this room, and then I'm like playing through, the bosses over here, some treasure over here. Kind of interesting, yeah. But I think what would make it even more interesting and make it feel more dungeon-like are if we add back few more lines at certain length from the starting point. So we can choose to put 3 more connections in. And these connections come from the candidates we didn't choose from. Remember we had A here and C here. Instead of throwing it away, whenever we don't choose something and discard the edges, we can say, okay, cycle candidates. We can say, okay, these lines are potentially useful for making our dungeons cyclic and interesting. And we can put like B, C, F, whatever. Doesn't matter what the actual name is. So then later we come back and go, okay, well, now we're going to actually randomly choose or prioritize based on some score and add back those connections to make, well, here I can turn left or right, but then it connects back here. Or you could have something like this where, you know, you have this like interesting connections. And that's the crux of how the algorithm works. I mean, this is basically how the connection determining algorithms work. But then, like, thing is, most of the dungeons that we create don't just look like this, right? We're not connecting them like this. Especially if you look at examples like Enter the Gungeon, you have something like this, where the corridors are very specifically shaped. Straight line, L, some of this shape. So we need to consider this as part of the thing. And in order to consider that, we have to go, okay, well, we're not drawing the line from the center. we're drawing from entrance to entrance. Each room has some sort of entrance. I mean, this one simply has 4 entrances, but some pre-con rooms might have like entrance right here and here. Or maybe these are options and we decide which one of these doors are our candidates. And so instead of doing all of this, we can say, okay, well, room can be represented as doors instead of rooms. And everything in the room can be already decided to be a connection. And then some other room down here would have some connections here like this. And then basically consider each of the entrance as the node, as opposed to the center of the room. So the change it's not that different. You're just considering the door, center of the door, and the entrance as potential connection candidate as opposed to the center of the room. And you can say, well, if they're facing each other, if they're close to each other, they're candidates. Or if you want to make it more interesting, you can say, well, we can randomly choose a connection. If it's facing each other, it's either Z or a straight line. If it's facing in the same direction like this, then we do this like double L shape, right? I call it double L because there's L here and an L here. If it's like this room connection, let's say these are the doors, then you have a single L connection, right? Because this door is facing here and this door is facing here. And then we can figure that out. Okay, so now that we've figured out what kind of logic we want to implement as a code, it's time to actually implement it in the code. So we're going to do that now, okay? All right, I know. Things are looking quite different from just a moment ago. I got a new lens. You know, I record the intro part and then the tutorial part separately. I have been pushing off the tutorial part for a bit because laziness, blame that. Not really, I was working on other things, but one thing I did do is update my camera lens, which makes it look a little bit fancier. So the background looks a little bit more blurry. I look more in focus. Let's get to it. We're talking about connecting rooms, right? We have been creating rooms and we have to connect it together. And we have a project here. So let's create a folder, and this can be your new project. It doesn't matter because I'm just making a collection of tool sets. You can have one off by yourself or by itself. It doesn't really matter. I think I like having Delaunay's Triangulation on its own. Delaunay Triangulation. If I know how to spell that, that would be wonderful. And then, as I said, always, because I do want to just drag and drop these functions or nodes in order to use them, I'm going to create a scene, specifically node, because the 2D-ness doesn't matter. So we'll say Delaunay Triangulation. You know, what's interesting about this is that I've actually did implementation of this for my own game at some point, and it wasn't for room connection, it was for star map creation. So I think I'm going to probably talk about that separately in one of the devlogs, or maybe it's already out and I'm talking about this one step late. But anyways, we're going to create a script for this one where we attach a script, and we're going to just name this class name Delaunay. Make sure we spell this correctly. Triangulation node. As we usually do, we're going to describe some of the functions that it needs to have. First of all, we definitely want to have a function called triangulate, which probably returns a result of triangulation. What is the result of the triangulation? So the returning variable or returning result, I guess that's the same thing. The result of the triangulation would be the edges that have been calculated, right? Technically, there's 2 ways to describe this. I'm thinking about either having a node object that has connections in them, or return edges described by point A and B. So for Delaunay Triangulation, I'm going to create either a resource or ref count it. I think it's probably better to be a resource, where we call triangulation edge. Because if I call it just edge, it might overlap with some other stuff. Triangulation edge, and this will be considered resource. And then it's going to take one variable that is point A, right? Which was going to be a variant, because it can be a node 2D, it can be something else. So we're going to have point A and point B. That's what describes an edge. One thing that we do need to do here, hold on. Oh, right. I suppose it needs to be variant. Let's say the triangulation edge is actually a node 2D. It doesn't like, resources don't like having anything that is node, child of node, any kind of like a scene related stuff as children for some reason. So we're just going to say, hey, we're going to have edge as a represented as a node 2D, which will have points A and B as node 2D. That's sufficient for now. So we have a triangulation edge. Only thing I don't like about this is that creating an edge is a whole instantiation. I can't just do .init or create new, which is kind of annoying. So I really want this to be a resource. Let me think. If I make this variant, would that work? It might. It might work better. It's okay. It should be okay. So I would say this is still Node 2D, and we're going to make sure this script is attached to an actual scene. We're going to call this a triangulation edge, which is a 2D scene. And we're just going to simply drag and drop this triangulation edge script here. So it's now connected, and it requires A and B here. Simple enough. Okay, so now that we have edges, we can say, hey, we're going to return just simply some triangulation edge as a result. We're going to put a placeholder here. Make sure we preload constant scene so we can initialize and create an edge when we need to. We're on version 4.5 of Godot right now, which means there's something called unique ID for resources. Before, it used to be like this. Where we go, hey, constant constant edge scene equals preload of, I just drag and drop the path, and then I can use this. The problem with this is that the path, when the path changes, let's say I move it around, this goes out of, date. Also, things can change, naming can change. So instead of relying on its actual path, if you delete this line, and then you just drag in, hold control and drop, then it auto creates this UUID preload constant for it. So now I can use this to instantiate a new edge. Now triangulate. What is the parameter for triangulate? We set this already. It's the points or the rooms or the nodes, right? So we'll say points, and that's going to be an array of whatever it is, node 2D, or variant. It's whatever you want it to be. And that's where we start. We do have to go back to the drawing board here. So we know, we talked about, and I mentioned the general concept of what Delaunay's triangulation is on paper. But we didn't really talk about how to actually do that programmatically. How does that actually work? It's not very obvious. There is an algorithm called Bowyer-Watson algorithm. Now, how do we prove that it works or not is not in the scope of today's tutorial, but I will explain the idea behind it. And then I'll explain what is required in order to achieve it. So I'm going to just open my Paint here real quick. One of the reasons why it took so long for me to get to the tutorial part of this video is because I was, looking it up, testing it myself on my other stuff to make sure that I understand fully. There's some maths, there's some trick, but you don't have to really know everything in order to do it. We mentioned that Delaunay's triangulation is basically it's a requirement where we say, hey, if you draw a circle, it's called Circumcircle, around 3 of the points, we want to make sure there's no other points within that circle, right? So this one would be failing the Delaunay's triangulation. Now, the Bowyer-Watson, I'm not sure if I'm saying that correctly, but Bowyer-Watson algorithm starts with basically when you have a bunch of graph here, right? Let's say these are the points. It starts with drawing a super triangle that fits all these points. This is a really bad triangle, but imagine that this is a really nice triangle. A triangle that is bigger than the space that the map occupies. And instead of having all the points all at once, it's going through the points list and basically adding it to the triangle. And it'll always be inside of the triangle, right? What that means is that once we add the point, we go through every triangle within the map right now. And right now there's only one triangle, and we draw a circumcircle, right? and then see if the point that just got added makes any of the triangle a non-Delaunay triangulation, right? So that means the super triangle now, because of this new point, becomes a bad triangle. All right, the super triangle is bad triangle. We're gonna take the points in that shape, the bad shape, and draw a line to the new point. Now we have 1, 2, 1, 2, 3 triangles, right? So these are the new triangles that has been created as a result of this new add. And, you know, I can sit here and try to prove it, but the idea is that if you do that, the resulting triangles are all Delaunay's triangulation. So this one will pass because nothing else is in here. And this one, if I were to draw a wonderful circle here, which I'm failing to do, would pass. And this one, right, because 1, 2, 3 here, would pass another Delaunay's triangulation. So the idea is you keep adding one more point, and then we figure out which of the triangles that already exist are bad, right? So 1, 2, 3 triangles here. If you do circumcircle here, this one is okay, it passes. If I do this circle right here, this one passes because this point is still outside of it. But as you can easily tell, if I draw this right here, it fails. So now we can say, well, this triangle is a terrible triangle. We need to redraw that. So we take all the terrible triangles, connect them all together as a polygon. This will make sense once again later. And then we draw a line from each point of the resulting bad polygon and then draw a line here. Now I keep calling it polygon. Why am I saying polygon here when it's clearly just a triangle? So we added this new dot, and what we end up getting is that if we draw this circumcircle here, this one, it failed, right? Because there's this new point that got added within this triangulation. So we would consider this triangle to have failed, first of all, for this point. And then if we look at this other circumcircle right here, technically this one also fails, right? Now we have multiple triangles that's failing, right? We have 2 triangles that's failing. I don't know if this one probably passes. So in this situation, what do we do? Because we're adding one point at a time, at any given point when the multiple triangle fails, the Delaunay triangulation passes or checks, there are triangles that are connected to each other. And the idea is we basically want to make a one single shape out of this, which means anything that's in between, we remove. So we're saying, okay, well, actually, the shape we're considering is this shape by getting rid of that middle line. Now, if we had an example where it's like, let's say we had something like this, where, point was here, so then all these 3 triangles are failing, then what do? We get the outer edge of this shape and only keep the outer edge of the polygon, which means we're deleting the inside polygon. And this makes sense why you have to do that, because what we're doing is that we're getting to each vertex of these resulting polygon and drawing a line to the new point. So in this case, this is what we get, like so. And that will make it so that the resulting triangle is Delaunay triangulation. Why am I explaining all this in words? Well, because, so if you search and Google Bowyer-Watson algorithm, a lot of them comes with this pseudocode, or they show the diagram, or they come up with this pseudocode. If you read it, it's not very obvious what they mean by polygon, edge, and bad triangle. I mean, this, you can try to understand it, or you can just copy and paste, but sometimes it's not very clear what it's trying to do. So it took me a little bit of time to just understand that, and that's why I'm sharing this with you. So basically, start with triangle, find bad triangle by checking Delaunay triangulation for circumcircle check for every single one of the triangles. If the new point makes it so that any of these triangles are bad, we put them together and make a polygon out of it where inside wires are all removed, inside edges are all removed. And then from each of the edges of the polygon, we connect them to the point that is being added to create this new triangle. And that's it. That's it. That's simple. There is a complication, which is how do we check if the dots are in the circumcircle? How do we calculate the circumcircle for the triangulation? That's one thing. Another thing is how do we make a polygon once we detect all the bad triangles? Those are the homework that we're going to have to solve. I did it once. So I'm hoping that I can do it again. And that's the homework here. So in order to triangulate, we are assuming we have a bunch of points that are given to us. Let's do this simply. First of all, in pseudocode or not, we have something like this where we say, hey, we're going to have a list of triangles that are being created by this algorithm, right? So we can create a new resource to describe a triangle. So I'm going to create a boom script and call it triangle. And this one is going to be a resource, class name triangle. And we're going to have some interesting functions we have to add in order to define this better. But for now, we're going to have it so that the triangle is going to have point A. It's going to have point B. And then it's going to have point C. And it can be anything, so we don't really have to type it, but we could always say this is a node. Or we can't do node 2D, can we? We'll do vector 2 for this one, right? Because all it is, all the 3 points within the triangle are basically vectors. Now, is there any point in doing ABC like this? We could just call this a polygon and then have the vectors be just array of vectors, right? And we just need to make sure that there's only 3 points in there. Is there something like that? We might actually. If we look at polygon 2D, that already has a definition for it. Polygon 2D, I mean, it has all the other extra stuff. So maybe it's like unnecessary. But yeah, if you need to use that, that's that. The triangle points would be an array of vector 2. Let's say later on, I want to distinguish between triangle 1 and triangle 2. How do we know if these are the same triangles or not? We know that by comparing, right? So I think we do need an equals function where it compares the triangle to another triangle. So we say other, which will be a triangle. And then we have to provide a fact that it is equal or not by basically sorting. And then I'm going to sort the points within the other triangle. So now we can assume that these are all going from either ascending or descending. Then if we go through each of the point and compare them, where we go, okay, well, points I, and then compare it to the other points I, they should be the same. If they're not, then we can assume that they're not the same triangle. If this is a little confusing, you can kind of sit down and think about it. But basically, the sorting allows me to go through each of the point in the array order to check if they're the same point or not. Now, obviously, additional check will have to be made where points.size needs to equal to other points.size, right? Because if the number of points do not match, they're not the same. So we'll say, let's make a variable saying that is equal is true. And then that one will say, hey, is equal will be continues to be true. Well, you know what? Maybe I don't do that. We don't even need to do all this. Basically, we're going to be doing some checks. Sorry, I'm like going all over the place. All right, let me delete this real quick. I'm going to paste this. But to help ease understanding, I'm going to remove the lines for now. If we say we're going to do some check and return false anytime the check fails, it'll immediately return false so that it returns a value really quickly. And only if it passes everything, then it will be equal. That would be the most efficient way to do it. So first check we do is, are they the same? So basically, if the size of the points do not equal to each other, that's the simplest check we can do, we'll return false. And then we're going to go through each of the points and compare them. At any point, if they're not the same, if the vectors are not the same, Because they are vectors, instead of doing it this way, if you do a vector minus vector, right, where it's pointing to the same direction, then it's going to do element-wise math, where x1 minus x2 happens and y1 minus y2 happens, right? And if those value are both 0, where we can say is 0 approximately 0, right? The difference between these are vectors. So we'll say the result is a vector 2, right? The result of the difference. And then we can say, hey, is that basically 0? If it is not, right? If it is not 0, if the difference between the two vectors are not 0, then we can assume that those two vectors aren't the same. I misspelled out there. This would be how you calculate if the triangle is the same or not. So we have the triangle comparison function already made. Another thing we can do is, just in case we want to hash this, if we want to hash the triangle, we can say, oh, hash code of this would simply be a stringification of the points. But we got to make sure it's sorted. Once again, remember, the whole point of hashing is so that it can be used as a key to differentiate between two different triangles. If two different triangles are the same, you know what? Do I explain this or not? I'm going to explain this. Okay. What am I actually worried about? Why am I overcomplicating this? I'm overcomplicating this because I'm not reading the document. That's essentially it. But you know dictionary, right? We use dictionary to key something to add value. If we say, hey, I want to dedupe, meaning we don't want to have more than one of the same triangle. And let's say I have a triangle object 1 and then triangle object 2. If I use this as a key in order to dedupe, how would they be considered different or the same? It would be wonderful if it automatically checks its properties value to dedupe, but it doesn't. In order to key it, what it's doing, all it's doing is that it's taking the object and then converting it to some integer number. And then it's using that as a code to populate that within the array. So if the code ends up being 0, then it puts it in 0 slot. If it ends up being 1, it puts it in 1 spot, etc., etc. And if it's bigger than that, it wraps around and then put it wherever it needs to. So the idea is that we're relying on the fact that the hash code of triangle 1 and hash code of triangle 2 would be same if the contents are the same, and would be different if the contents are different. If I don't make my own hash code, what happens if I just say, well, I'm just going to use triangle 1, whatever resource it is, as a key, versus I'm going to just use triangle 2 as a key? What happens? How does it determine? Typically in programming, especially so in Java, these data structure or these data is represented in the memory, right? I mean, we talk about memory a lot. And basically, whenever we are creating an object, this has some sort of blueprint where it says, well, triangle requires this much section within the memory. So this will be a triangle, triangle 1, and then it has some information in it. And then it'll say triangle 2 is over here. Now, it's awfully convenient because the address in the memory, which is the slot where the triangle lives in, happens to be a number. It's an integer number. So if we use the address slot as our key, by default, it differentiates between triangle 1 and triangle 2 without having to do any fancy logic. So when there are two separate instances of the object, it'll always be hashed as two different objects. So even if triangle 1 has same ABC point as triangle 2, because they are two different instances, they'll be considered a different object. So we need to not rely on the default behavior, but rely on our custom behavior. Now, reason I'm converting it to string is because, fortunately, dictionary string, it does the value matching. So as long as the string is the same, it does the same. So what we're going to do here, if we stringify an array, it prints it out in order, whatever is in the content. So if we sort it and then we stringify it, meaning we represent it as a string, hopefully that gives us an appropriate hash code. We can check this real quick by starting it out real quick. I'm going to comment this out, and we're going to make a ready function to test it. So let's say we have an array of vector called vector 0, 0, vector 0, vector 2, 0, 1, and then vector 2, 1, 1. And then if I print this out as a string version of it, what would it become? So let's launch this. I want to see what happens. This is a testing. It says it in this way, right? You know, further testing could be done this way. Let's say I make a second array, and then I'll change the order of the points here. So we have this point here and this point here. They're simply different order. And what we're going to do now is I'm going to sort these two arrays separately, and then print the stringify version of these arrays. All right, I launch it again, boom, and we got exactly same string. So we can say if we do a sort and then the stringify of that object, we can reliably say they will return a same key as long as they include the same points. So this will work. We can say hash code, and it's going to do all this fancy work, and we're good. We got the equals. I feel like this was an overkill. I think it would have been fine if did this, because alternatively, what we could have done is instead of doing this, we could have just said, this is cleaner, right? So we can say hash code equals others hash code. As long as they're the same, it's considered the same. And it's just a string comparison. And that's simple. All right, so we have a triangle. We just made a basic triangle, but these are the things we need to do. You know, technically, honestly, because this is just an array of vectors, I could even use this as an edge as long as I just populate only 2 of them. I might do that. We'll see how that goes. Okay, so we're coming back to Delaunay Triangulation here. We're back to the triangulate. First thing we need to do is basically have an array of triangles that we're going to use, which will be just triangle here. And the first step is to create a super triangle. So we'll say get super triangle. Once again, super triangle is a triangle that contains all of the points, however that is done. So given the points is going to create a super triangle, which will be described as a triangle. And then we're going to do this in a bit, but for now, it's simply a new version of the triangle, right? Because it's a resource, I can just simply new it. And I'll actually implement this in a bit. And so the idea here is that triangles will start with one object in there, which is get super triangle of the points. And then for each of the point, we're going to add this new point into the system. So we're assuming that we're adding a point here. So we're going to say, check if the new point is making any of the triangle failed Delaunay check, triangulation check. Basically, for each triangle in the triangles, we're going to try to say if is Delaunay triangle, and it fails. If the point that we're providing fails this check with the triangle, then we're going to say it is a bad triangle. We're going to add it to the bad triangle. So we're going to have, for this one, bad triangles will be added as an array of triangle. And basically, we're going to be adding the bad triangle into the triangles. So that means we have another function we need to implement, which is check if it is Delaunay triangulation. So we have a point, which is a node 2D. And then we're going to have a triangle here that we're testing with. And then it's going to just simply return a Boolean value saying it is either Delaunay or not. And that's one thing that we're going to have to do there. I spelled bad triangles wrong, so we're going to do that. Okay. So first thing first, we said, hey, whatever doesn't pass the triangulation, we're going to add it to the list of the bad triangles. Cool. We did that. And then the next step would be, don't worry, we're going to implement all this later. I'm just trying to put the structure down first so that we can easily fill up everything while tracking. And, part of this is also checking that I know what I'm doing, even though I should know what I'm doing already because I've done this already. I'm just kind of thinking about what I need to do as I go as well. We need to get rid of the edges. We need to create a single polygon of edges to create this new triangle. Now, this one might be interesting. This might be a little tricky. Basically, we need to, for each of the triangle, we need to make sure we get rid of any of the edges that are inside. The edges that are inside of the polygon, what do they have in common compared to the outer edges? And that's the question, because how do we identify the edge that's inside of the polygon? It's simple, actually. If we break this connected triangles apart, it's basically these triangles put together, and the part that needs to be removed are parts that are shared within different triangles, right? All the outer edges are unique. They're not shared by any other bad triangles. But the edges that needs to be removed are all the edges that are shared between different triangles. So basically, we want to go through each of the bad triangle, and see if any of the edges are in other triangle. If it is, we want to get rid of it. Alternatively, we can go through each of the triangle and then pick out the edges. So we say, edge A, B, C here. We can put A in the list, B in the list, and C in the list as part of the edges that can connect to the new point, potentially. And then we say, if we go to the second one, we see that we have D, E, and C here again, right? When we're checking the second one, we say, C already exists. Then we will have to go, C can't be part of that. And then add D and then E. And then go through the next triangle and we check B, F, G here. We can say, F can be included, G can be included. Seems like B already exists. We got to get rid of the B. Now we have all the edges that can be used as a new triangle for this new point. All you have to do is connect the edge to the new point, connect the edge to the new point. So we have a bad triangle. As you said, we're going to go through each of the triangle and collect the edges, and we need to uniquely identify the edges, but that's okay. We already know how to uniquely identify the edges, right? We say var new edges. This is a dictionary. Dictionary of the string, which is the key version of the vector. And then we're going to actually put triangle as a value. Shouldn't it be edge? Why is it a triangle? Well, what I'm going to do is I'm going to pre-create the triangle and only populate 2 points. 2 points belonging to the edge that I'm adding. How about new triangles? And these will be partially made triangles. And we're going to go through each of the bad triangles. Bad triangle in bad triangles. Edge A would be a new triangle. Right, triangle new, and then edge B will also be a new triangle, and then edge C as a new triangle, right? And then we got to populate them. Well, they have points. We're going to add the 2 points, which will be the bad triangles points A, bad triangles points B. And then we do the same thing for, I guess we should collect it into a single spot here. We'll do all of them all at once. We'll do it down here. And then we're going to do that basically same thing for edge B and edge C, like so. Right? We have edge A, edge B is 1 and 2, right? That's the second point and then the third point. And then the first point and the third point would be edge C. So we have 3 edges here, and we created 3 different triangles with only 1 edge, only 2 points in it. And the reason I'm using triangle here is that we can use triangle's hash code because it doesn't care about number of points in it in order to key it. So we'll say, okay, well, here are the new edges. In the new triangles, we're simply going to say edge A hash code will equal to edge A. And then we're going to do that for all of them. But there's one more check, right? We said basically before adding it, if the edge already exists, we got to get rid of it. So basically we go, if new triangles has, right, this code, edge A code, that means it already exists. That means we got to skip doing this. Not only do we skip it, we got to remove it. Go to the new triangles and say erase the value that belongs to edge A. Otherwise, we're going to edit. And then we do the same thing for all the edges here. 1, 2, 3, 1, 2, 3. And we're going to do that for edge B here. And we're going to do that for edge C here. I mean, technically this could have been a helper function, but it's okay. So let's check this real quick. So in the new triangles, we're going to check if the edge, the new triangle, already exists. If it does, we're going to get rid of it and not do anything. If it doesn't, we're going to add the new edge to it. And we're going to do it for each of the edge of the triangle that belongs to a bad triangle. So now we have new triangles that are basically all the potential edges that I could use for this new triangle construction. I know this is like really overwhelming sometimes, but I trust that you guys are understanding it. Part of this is the pain of just thinking about this systematically. If you have any question, if there's any confusion, make sure you share it with me. You can come to my live to ask any detailed question too. I'm live on Monday, Wednesday, and Friday. Pacific time. The time is a little bit confusing. You can go to my Discord because I do make an announcement when I'm planning on going live or when I need to cancel. And you can just ask your question there and I'll try to answer it. Okay, so new triangles. We said the first part, the keys are just the hash code, so it doesn't matter. All we need is we need to go through the values. New triangle in new triangles values, right? We're going through each of the triangle. And basically, we're going to have to get the points there and push back, insert the new point into this triangle. So we're going to have to do that for now. So new triangle points pushback will be the testing or adding point, which we didn't define yet. So don't worry. So we're going to come over here and we're going to say var adding point, which is a vector 2, will be point.position because point is no 2D here. So we're going to grab its position and use it as a point. And instead of doing this like this, we're going to check the adding point, which will be, we're going to have to rephrase this so that it's vector 2 here. Super triangle is okay. Sick. I think this will be okay. So we have adding point here. We're going to add the adding point to the new triangle. Now we have all the triangles that needs to be added into the final collection of triangles for the next iteration, right? Here's the thing. We are going through all the triangles on every loop, right? And we identify the bad triangles from the collection of triangles. And then we want to add the new triangle into that collection of triangle for next pass. Which means there's one more job to be done, which is we didn't get rid of the bad triangles from that collection of triangles. Now we can go through each of the triangles again and identify which of those triangles equal to the bad triangle and remove it, or new triangles as a, I guess we'll call this updated triangles as a new collection. And basically do one of these where we go through the triangles and whatever passes the test, we will add it to the updated triangles list, right? Because Updated triangles list will be containing all the triangles that should be on the next cycle. And then we'll just simply skip adding the bad triangles. It only adds to the bad triangles. And then later, when we're creating a new triangle that's finally created, we're going to add that new triangle into the updated list. And then before ending the loop to go to add the next point, we simply say, well, the triangles that we're going to test on just simply equals to the updated triangles that we created. And that's it. So we have all these things and it creates it, and it does the triangulation. And at the end of the day, we have a resulting triangles. We have the resulting triangles. I know in the beginning we said we're going to treat the resulting thing as just the edges, list of edges, or we could just return the triangle. Whatever is using the triangulation logic can look at the triangles and do a mapping between the vectors of the triangle and the point themselves. That's not my problem, right? That's the client's problem. So we can do that instead so that we can be done here and just return the triangles at the end. So that's the triangulation logic. There's a chance this doesn't actually work. There might be a bug, but we'll find out. Not a problem. So now we actually need to get to this part where we create a super triangle and then we check if it is a Delaunay triangulation. How do we create a super triangle? That's it's pretty easy actually, because we don't really need to be specific on how big the triangle is. We just need to cover all the points. We got to make sure all the points are within the triangle that we create. Based on the extremities of these positions, you can create this like rectangle that contains all the points. And if we say, hey, you know what? We can actually create a triangle that goes up at the center of this rectangle, and then that borders this corner right here, and another one like this. And then at the bottom, you can just have one like this. This is an isosceles triangle because we're splitting this rectangle into the equal distance here. And this corner from here to here is same distance, from here to here is the same distance, right? This triangle can be calculated, first figuring out the bounding box. And once we have the bounding box, we can find this point. And once we can find this point, can we find this point? Yes, we can actually. All it is double the height. If this is height of h, then this is also height of h, which means this point is middle of x. Let's say this is x left and then x right here, let's say. Then this is like the midpoint of this. And we know midpoint calculation from trigonometry back in the day, where xl, xr, and then divide by 2. That'll be the x position here. And then the y position is simply, if we're assuming that this is h, this will be the h times 2. What about this one right here? This one actually happens to be also exactly the same length as this, where we take this and then we go another step, starting from this, which is this one right here. Starting from this point, this midpoint, we're adding half a width, and then we're adding another half a width. So essentially this point is midpoint, which is xl plus xr divided by 2 plus the width. And then the y is simply y bottom. And then this one is the opposite, where xl plus x right divided by 2 minus the width of the square, yb. You can check my work, but essentially that's what it comes down to. Now, I don't know, I don't feel comfortable with this calculation. You might have a point that's right on you definitely will. You will have a point where they are right on the edge of the square. And that means you could have these like boundary box that's like perfectly squared up against this super triangle. And I don't feel comfortable with that. So I actually want to figure this rectangle out and give it some margin to make that square slightly bigger, so that when we draw a triangle around it, it'll be giving a healthy margin there. So let's say lowest x value, which will be, let's say we'll make this 0 to start with. And then we want highest x value. And then we want lowest y value. And then we want the highest y value. We just simply go through each of the points, point and points. And then because it's no 2D, we grab its position. So we'll say, hey, position here. And we're going to compare it to the lowest and the highest. So if the lowest x, or if the position x is lower than the lowest x, then we're going to say lowest x will equal to position x. And we're going to do that for basically each variable that we're trying to find here. And we're going to have to update that. So I copied it 4 times. Next one is if the x position is greater than the highest x, then we're going to make highest x the x position. And then we're going to do the y. If the position of the point, oh, I need to update this. Whoops, I misspelled it, by the way. It should be point, not points. So let me do point here. Point, because points are the arrays. So I'm updating it to be point, singular, not plural. So the lowest y will be the y if it is less than the lowest y. If the point's position y is greater than the highest y, then we need to update the highest y to be y position. Now we have a bounding box. We have a bounding bounding boundaries, I guess. Now we want to create a super triangle, which is a triangle, which is a triangle.new. And that's what we're going to return at the end of the day. And we want to add the points. We want to calculate the points here. First of all, I'm going to add some margins here. So we're going to create margins. Boop, boop. Add margin, where basically lowest x will grab I suppose I could define a margin here. Var margin will be float, and we'll grab a margin of, I don't know, like 50 pixel. That seems pretty healthy. So we're going to add margin and minus margin to each of the values here. Oops. So that we give it a pretty healthy gap. And then middle top point, right? So we want to look at the x middle point. So it will be vector 2, x midpoint, boundaries width, right? Or boundaries height times 2. That's what we said this is, right? So that also means we have to do a little bit of math here. So we have x midpoint will equal to, we said that is the lowest x plus the highest x divided by 2, right? And then we have the boundary height. I mean, technically boundary height, we could just say boundary size y, like so. So we can say boundary size equals to vector 2 of, the size is difference between the highest and lowest, right? So we'll say highest x minus highest or lowest x, and then highest y minus lowest y. And that's the boundary size. So first point is x midpoint, and then the boundary y double. Second points are, we said, essentially from the midpoint, we're going to go left first. We're going to subtract the size of the boundary. And then the y is simply the lowest y. But we got to be careful here. On the game engine or on programming, the lowest y is actually the highest point, right? Because we go from negative to positive. As you go down, the y value increases. So actually what we're looking for is the highest y will be the y value, and then we go left to the size of the boundary box. And then the third point would be x midpoint plus boundary size plus x. And then that'll still be on highest y, and that will be our super triangle. We can test this out, I suppose. Let's make a tester real quick. Scene triangulation tester. And we have it here. It's just a 2D node. I'm going to create a tester script here. Essentially, I'm going to drag and drop the triangulation here. That's what we've been doing. And I'm going to drag and control drop so that it does the onReady here. And basically, as soon as a ready pops up with the triangulation, I'm going to say get super triangle, and then we're going to provide points. We'll have to generate random points too. So we'll say var point count could be like 20 here. And then for I in point count, we're going to create points, which is array of no 2D points, pushback, no 2D, new. So we're creating a new node 2D. And we also want to randomize the points location. So we're going to say points position will be vector 2 of x position that is random. I in the range of, let's say, I don't know, 200 to 600, or maybe even better, 500 to 700. And then random I range of 500 to 700. So it's going to be some random spots. Well, our new point will equal to no 2D like that. Like so. New point, not points. Then we're going to add it to the array here. Maybe we could even make a global function of that. So we'll say points here will be array of no 2D, and then get rid of this instead. And we're populating the points, and we're going to do Delaunay triangulation. So we'll say test triangle or super triangle will be triangle. And then this one will equal to this. And basically, we want to do a draw function where for all the point within points, we'll draw a circle at position of the point, and it's going to be a radius 2. Let's say color. That LS blue is fine. You can choose whatever. So we're drawing a circle on where the points would be. And then if we have a super triangle, if super triangle exists, we want to draw a polygon. I suppose to say polyline rather than a polygon. And we're going to provide, this is expecting a pect vector of 2 array. I think that can just be the points. I don't know if it immediately converts or not, but I think I can just provide the points here because that's the array of vectors. And we'll say this is a red triangle here. All right, so we're going to generate random points, and then we're going to run the super triangle, and we'll be able to see where the triangle draws in the context of the points. Okay. Something's definitely happening. I'm not really sure if the polyline is working here. If I recall correctly, in order to create a full polyline as a triangle, they need to wrap back around. So I believe I actually need to make a array that includes the point A again. Polygon will be array of vector 2. So we'll say super triangle points 0, 0, 1, 2, and then 0 again. So we'll do 1, 2, and then 0 again. And then that's what we're going to add. And I want to see that almost. Something funky is definitely happening over here. So we'll have to test. I have a feeling that I definitely messed up some sort of like Y being flipped around and stuff like that. There's a sense of little bit of an offset. I almost feel like the bottom part is right, but then obviously the top part is wrong. And you probably caught this already. When I'm doing the above triangle, where I'm doing double the height, I was calculating as if up is positive, right? So where we said boundary size Y times 2. Well, boundary size Y times 2 from where? What's the starting point? Actually, it needs to start from highest Y point plus boundary, or lowest y point plus 2 boundary. So we got to go highest y, which is a misnomer because highest y is a lowest y. So we're going to actually use the lowest y plus boundary size as our y, I think. I think that might fix it. We'll see. Okay. It's gone altogether. Oh, it needs to be minus because remember, up is minus. This is very difficult. Okay, kind of. That's a huge triangle. So for margin, we're taking more out and we're adding more. So margin calculation is correct. You know what? This is a mistake. I gave it a precondition of 0, and that's the mistake. 0 is at the edge of the screen, right? Y equals 0 is on the topmost, and I'm making the points down here. And none of the points will beat the 0, right? It can't. So what I actually need to do is, instead of relying on just the value, we have to go, hey, if this is the first time populating it, we have to give it a position. Technically, I think instead of giving a random 0 as a value, we could just grab a point. So points 0, and then do a position and give that x value as a starting point. Because, I mean, that's essentially what we need to do. Only time this will fail is that if this is empty. But I guess if we say, hey, if points is empty, we're going to return null because there's nothing to calculate. And of course, my camera just died. But let me finish up drawing the super triangulation, and then I'll charge my camera, and then I'll be back. It's just simple as that. But yeah, so I made that correction. I think that will fix it, actually. So that's the most important part of it. So let's run the tester again. And voila, look at this. We have a bunch of points, and we have a triangle that encapsulates those points in a predictable manner, where if we imagine this is a bounding box, we have a 50 margin and we have a super triangle. All right, I'll charge the camera, I'll be back, and we're gonna jump right into doing the Delaunay triangulation check, which is basically the fun part where we draw a circumcircle and then see if the point passes that or not. Okay, we gotta get this going. We don't have that much time. There's actually a lot to cover. A little disturbing how much we need to cover before I can say we're done here. I think potentially for this video itself, I might have bit off more than I could chew. I don't want you guys to be scared of the prospects. Next thing we want to test is drawing the circumcircle around 3 points that are present. How do we do that? You know, honestly, you could search it. You can say calculate circumcircle with triangle or something like that. And you can figure out how to do it. There's a formula for it, but I can give you at least a concept. I can give you the concept of how you would calculate that yourself as a fun exercise. I mean, also it helps to know. So like, let's say if a world-ending event happens and then you need to come up with ways to calculate circumcircle again with a triangle, you'll know where to start, right? I mean, that's what it's all about. We're making games and we're watching tutorials so we can make games when the world ends. So I'm going to just simply describe the concepts without actually doing the math. If we have 3 points and then we draw a perfect circle that fits this triangle, this is not a very good circle, but assume that it is. How do we figure out where this circle is and how big the circle is, right? Because circle is described by the position, center position, X and Y, and its radius. So given these 3 points, point A, B, C, figure out the position and the radius of the circumcircle in relation to the center of the circle. Now, of course, this is not a perfect drawing, so it's harder to tell, but if you draw and find the midpoint of this segment between the lines, and then draw a perpendicular line, right? A straight line that is perpendicular to the midpoint. So we have a line here, and then we find a midpoint and then draw a perpendicular line or this one as well, midpoint, and then draw a perpendicular line, that line goes through the center. What does that mean? That means if we can somehow figure out the formula for this line and formula for this line, it's a simple algebra or trigonometry, right? Because we've done that before where we have formula for a line and then another formula for another line, B2. And then we can say, well, some of those values we can figure out to fit in. And then we can say, well, let's find a y where these two lines are equal to each other, right? In order to find a perpendicular line that goes through the midpoint of the segment, how do we do that? Well, first of all, we know this line is going to follow some y equals mx plus b, because that's the equation for a straight line on a graph. And in order to find this line, we know that the m is a slope and b is some constant we need to figure out. Well, the slope is actually pretty easy because the slope of this line, the perpendicular line of AB, would basically be flipped slope of this line right here, right? Perpendicular line slope is just inverse negative. Slope is what we call a delta y over delta x, right? Depending on the graph position, but basically rise over run is what we used to say. So that's the slope. So what is the slope of AB on a graph? Slope of A and B, this line, is this value over this value, x prime over y prime. Or, whoops, I guess I should call it y prime instead. Y prime over x prime, let's say. And what are these values? They are xa, ya, if we're assuming point A is described by this coordinate, and point B is described by this coordinate, which will be given to us, some number. I keep misspelling these, yb. Then we can say the x prime is just difference between xb and xa, right? In this case, it would be xb minus xa would be x prime here. And y prime would be yb minus ya. And then you can just take that and find our slope of segment AB minus ya over xb minus xa. So the perpendicular line would just simply be, I mean, you can trust me on this, but basically you invert them, meaning you take 1 over m, or you flip them, xb minus xa over yb minus ya, and then you just negate them, because now it's going the opposite direction. So the rise over run becomes run over rise negative. I mean, that's just kind of the rule. You can look at the proof of why this is the case, but you can kind of intuitively see that is the case. If we look at this type of line, for example, you can see that this line looks like that, you know? So you calculate the m that way, and then once you fit that in, once we say, well, we know this perpendicular line has that negative 1 over m, and then x, and then y. Next mystery is, how do we figure out b? Well, we can figure out b by, well, first of all, 1 over m is an actual number. And we can say, well, this line goes through this point right here, the midpoint between a and b. And we can figure out the coordinate of a and b, right? Coordinate of a and b is simply b plus a divided by 2. And now that we have x value and y value that goes through the line, we can just plug it in, right? Plug it in and then calculate b. Now you have a perpendicular line formula. So we now have 2 perpendicular lines for the segments, right? This one is perpendicular to A and B, for example, where it's like this. And then this one might be perpendicular to B and C, for example, this one right here. This is a bad drawing, but you get the point. You want to find a case where y is the same and x is the same for both of the line equation. And you can do that by, saying that this y is same as this, so you can equate to each other. There are many techniques to figure it out. Essentially, at the end of the day, you get a formula. I mean, this is one example here, but essentially you get something like this, where u of x here is talking about center of the circle, x, and then y here is the y value of the center of the circle. And then you get this complicated formula where d is replaced by this, where ax is, obviously point A is x, b is, point B, c is so on and so forth. A little bit complicated, so they simplify it by, luckily you don't have to use that complicated formula. I mean, it's still complicated, but it's a little bit better. This circle usually lies on xy coordinate like this, right? And basically what we're doing is that let's shift the circle over so that the furthest left corner, or point A, lines up at origin, right? That means we're shifting it by delta x and delta y, right? This is the offset. And then you can calculate some circle here. Let's say we calculated some ux and uy coordinate. So then the actual result will be just basically, well, initially we shifted by this much. Now we can add that back in. And then we'll get the actual circle center. And then the radius calculation will be the same, right? Radius is the same no matter where on the coordinate it is. So reason this helps is because if we set the A, for example, of these 3 points to become 0, 0, look what happens to the formula, right? You can replace all the A's as 0, which gets rid of a lot of these. And what you get is this one right here. You see as a U prime here. You see how all the A's are gone? Because they have been shifted to make it so that point A is the origin. After you calculate it, right, ux and uy prime here, this says it right here in the Wikipedia, where the circle's center, circle's coordinate is this shifted circle plus A, because that's how much we're shifting it by. So essentially all we have to do is formalize the calculation by copying these over. And this ends up being pretty simple. I've already done it here, so we can... Well, I haven't done it already, but I'll have to copy and paste it from my other implementation to make sure I don't make any mistakes. Before doing a Delaunay triangulation, we have to say func calculate circumcircle, right? And then we are trying to find a circumcircle of a triangle. And then it's going to return a circle. And circle is not a thing in Godot, right? Well, it doesn't naturally have a regular circle object, which it might actually. If they do, let me know. I haven't found one out yet. So I'm going to create a new script. Have we been using resource? Yeah, okay. So we're going to use resource again. So we're going to create a new script within the Delaunay Triangulation 1. And then we're going to call this a circle. And then we're going to open it. And it's going to be resource, extending a resource. And we'll call this a circle. And what does a circle require? Circle is simply a combination of position and a radius, which will be a float. And that's all we have to do. Oh, I misspelled resource here. Boom. So we have a circle now. So that's what we're returning. We're going to return some new circle. And basically, we're going to do that calculation that we were talking about within this function, which we will call here and then check. Okay, here we are. It's both simple and complicated. I set the code line separate enough for you to be able to tell what's going on. Essentially, here it is. The first thing we do is we create a circle that we just, instantiate whatever, make an instance of a circle that we just created. And then this is an interesting one. We're sorting the points within the triangle with a custom method, because I don't trust, when I was doing the hash coding, I trusted that the points will be sorted in ways that will make sense for hashing consistently. But I don't actually know how the vectors are sorted within an array. So just to be safe, I wanted to make the points so that they're aligned from the smallest x to the largest x. So it goes from left to right. Reason I'm doing that is because, once again, I said I'm going to offset it by point A, and I want to make sure point A is the one that's furthest left. It's not, I don't think it matters as much, but just in case I'm doing that so that everything else is nicely edited as opposed to having to do this other things. So we're doing a sort custom, and then we define what the offset is. And the offset, once again, is point A. And then now we're creating point ABC vectors, and then we're offsetting them by the offset that we have been given, which is basically point A. And then the position X and Y calculation here, this is pretty much a copy from that Wikipedia page straight up. You can see a little bit complicated here. Bx squared plus by squared. And then you multiply all of that by cy. And then you subtract that by cx squared plus cy squared times by. And then basically, you know, this part is where I'm dividing that result by this value because that's what the formula calculation does. I could have as easily done it over here, but that seems a little messy. So I decided to do it as a separate calculation. So we're doing the top part first, and then we're doing the bottom part calculation, and we're dividing it by that much. And the y as well over here. Oh, I guess you couldn't have seen this part. So the end of this is cx squared plus cy squared, multiply all of that by bx, minus blah, blah, blah. And then this is a thing, whole thing. And then you divide that by this much, which I guess it's the same value. I see that I do it differently. Anyways, you get the point. So do that. And then the radius calculation is, there is a radius calculation in that Wikipedia as well. You can get it correctly, but essentially radius would be distance between the circle's center and any of the points. It should be the same everywhere. Matter of fact, that's what I did to confirm that the circle is correct. When I was debugging it, I said, okay, well, let's see if the distance between all the points, A, B, and C, is the same. Distance from all the points from A, B, and C to the center of the circle is all the same. Because otherwise it's kind of wrong. And then of course, don't forget to undo the offset of the position. And now we have a calculated circumcircle. Okay, cool. So now we can create a circle based on the triangle. So we can say, all right, when we're doing a Delaunay triangulation check, we're going to call the circumcircle formula. And this is going to create a circle, right? Circumcircle, for example. As a circle. I don't think we have to do that part. And this one, how do we check if the point is inside of the circle or not? Any idea? Well, I did it this way. You don't have to. But basically, if the distance between the point and the center of the circle is greater than the radius, then it's not in the circle, right? I'm going to do a distance check where I do from the point, calculate a distance to the circumcircle's center position, and then we're checking if it's Delaunay triangulation, meaning it passes. So it will pass if that distance is greater than the radius of the circle. So we have this properly calling, and then it does all the things that we've done before. So technically, we should be able to see that it's working properly. We can try to debug this by doing a visualizer. We don't have to. It makes for a good visual stop for the intro to the video. So I guess I could just do the visualization for our own fun sake, and then we can use that for intro to the video. So that I guess by now you've already seen the result in the beginning, but this is how we made it essentially. What I want to see is I want to see each of the points get added to the map and they get newly drawn. And then once they get drawn, anytime we're checking the Delaunay triangulation, I want each step to draw the circle one at a time. And then I want to show the edges basically disappear and reappear maybe. I think that's some of the ideas. So let's do this. We're going to say we're going to have a signal for point edit, and that's going to give a point. And then we're going to say circle drawn, and this is a one-time circle drawing. And then we're going to say new triangles drawn, which will be a bunch of triangles, array of triangle. Of course, triang is not how you spell triangle. The progress of the calculation stops until we call next, right? So we'll say next step, and we're going to do something here. And that, I think we're going to do it by creating another signal that says continue. Or I guess we shouldn't call it continue because continue is a word that's already being used. We'll just go next. How about that? Signal called next. And essentially when next step is being called by external, we'll just emit that simply. And basically we're going to add all of these into here. First of all, point edit. We are adding a point whenever we are observing a point. So we're going to emit adding point here, and then we're going to wait on next signal here. So we're signaling out, and then we're waiting on the caller of this project to say next. Next one, circle drawn. We're drawing a circle every time we are calling calculate circumcircle. So I think what we can do that right here, where we go circle has been drawn, where we emit the circumcircle here, and then we could await here. But the problem is that this function is being called without an await. So I think what we can do, await on this, and over here we can say await on next, like so. Next thing is new triangle edit. And so we'll go, oh, new triangles have been drawn over here. Sorry if my mic is drifting away a little bit. I know setting might be a little bit different from yesterday, and this is the downside of not doing everything I need to do in a single session, but can't be helped. My camera died yesterday, so not that you need to see my face for a tutorial. Matter of fact, I wouldn't be surprised during the edit if I get rid of my face entirely. But I got a new camera or a new lens. I have to show it off. All right, what are we emitting here? We're emitting the resulting triangles here. So it's going to be emitting the entirety of the triangles that needs to be drawn, like so. And let's see how that works out. So in this tester, once again, we have the triangulation tester open, right? That's where every drawing operation is happening. We're going to go to Delaunay Triangulation here and click on node, and you see all these signals that are out here. So what we're going to do is basically connect each one of these to the tester. I'm double clicking everything except next. Function input event, which is input event. And then we're going to say if event is action pressed, UI accept, then we're simply going to say Delaunay Triangulation, next, emit. And rest is history. Now we just got to make this draw our little circles and dots so that we can test things appropriately. So we already have a draw function here, and we're drawing all of the points here. Instead of drawing all of the points, we can make it so that we register points to draw. So we say draw points, array of vector 2. And then the next one is draw triangle, which will be array of triangles that we're going to be drawing. And then we're going to say draw circle as the next thing. Since we're drawing only one circle at a time, we can just make it a single circle here. Under the draw operation, we don't need this anymore, so I'm going to get rid of all this. Well, before I delete it, let me copy some of these logic over so I don't have to redo it. Basically, for each of the entity that we just created, we go for point in draw points. We're going to draw circle, right? And then we just have to change this position to be point, because point itself is a vector. Oh, whoops, I made a mistake. Draw circle is a function and also a property, so it's sharing a name. We have to probably, you know what, I'm just going to put underscore on them for simplicity. You can name it something else. But this way, nice. So this will be good for drawing all the points. Probably will draw only one point at a time. For the triangles, we're going to go for triangle and draw triangle. Since this is a triangle, same thing as super triangle drawing. We're going to bring it up here. and basically do this logic that we've done earlier for drawing. And we're going to draw a, let's say, green triangle we're going to draw. And then lastly, we're going to draw a circle. Draw a circle. Basically, if it exists, we're going to draw a circle. And this one is not going to be filled. So we're going to say draw circle position, draw circle radius, and then color. Let's say for this one, since the dots are blue and triangles are green, we can do red. How about that? Red for checking. And then we'll do false for fill so that it only draws it, draws the outline of it. Cool. Given the information, it'll draw one step at a time. For circle, that's simple. We just say, hey, draw a circle equals the circle that got emitted. And we're going to just Q redraw. And basically, we're going to Q redraw for every single one of these emission. For the triangles, we're simply going to equate that as well to the triangle parameter. And lastly, for the point, now we have several points here, or options here. We could just keep adding to the collection. I don't know why I said we could. We should. I mean, that's it. Let's see how this works out. I have a feeling it might not work out in the first gecko, but that's the fun of all this. By now, you should know that we are really not afraid to debug. Sometimes I'm embarrassed. Sometimes I'm embarrassed when things don't work out. But, you know, that's kind of, also, lastly, most important thing, we need to actually call the triangulation logic. So we created the count. Instead of getting the super triangle, we're doing triangulate for the points. That should work, right? It's yelling at me. Why is it yelling at me? Oh, because the result is not a triangle. Yeah, that's fine. Like so. Cool. Let's run it and see what happens. We might need more information, but we'll see. All right. First of all, as soon as I called it, it drew a super triangle. Great. Next up, a point has been added. A circle will be drawn. Oh, it doesn't like that. It's saying that the circle... Oh. What is it saying? Invalid assignment of property key radius. Radius doesn't exist for the circle. Let's take a look. Radius does exist. So why is it saying that is not a thing? A, distance to circle's position. Property or key radius with value of type float on base object circle. Distance to returns. Did I misspell radius? I did. All right, everyone. Hopefully you guys didn't make this mistake. Radius is spelled with D-I-U-S, not radius. All right, here we go. Relaunch again, and let's check if this worked. Spacebar point. A circle is about to be drawn. It's saying that I can't do that again because I, once again, misspelled radius here. You think I should know by now. Anyways, boom. Circle is great. That's a great circle. And as a result, what gets drawn? Another. Hey, look, we're getting through it one at a time. This check is failing right now because it's saying the key. It's another. Where else did I misspell radius? Now, at this point, I feel like I need to search it. But once again, I trust myself a little too much. All right, circle has been drawn. New triangle. Next point. Okay, right here. And then circle is going here. That fails, right? Remember, this circle and this point occupies inside of the circle. So this triangle should be considered failed. This one also considered fail, meaning we should be drawing a polygon between these two triangles. So this middle line should go away as a result. And this one passes. So as a result, we get a triangle. Boom, right? We got a new triangle that gets rid of this middle line and then adds a new point. Next point is getting added. And we're doing some circle check. All these are passing. This one barely passes, but it does. And it's lovely to see the circle actually drawing properly. And we have that. And a new point is being added. like so. And then I can just like keep pressing spacebar until at the it's over. And this is pretty cool. Look at that. Now, I'm going to just keep pressing spacebar here because I do want to show this animation in the beginning. Maybe we can fast forward this part. But the point is that it's working. And it's beautiful. All right. Maybe 20 points were a little bit too much. Well, at the least, you can visualize how long this process actually takes because we're drawing a circle for every single triangle that gets generated. But you get the point. Pretty cool. Points gets added. The new triangle gets drawn. Instead of doing all of this, we can get rid of the awaits here. Await next. Get rid of all the await next. Then it should happen almost instantaneously. Let's see. Look at that. It drew everything all at once. So now we have all the points and all the triangles. It's missing this last one because we did the triangle emission only in the beginning. So if we do it at the end again, we should get an actual resulting triangle. Great. Look at that. We have a neighboring thing. Now we're missing something. What are we missing? Well, technically these super triangles or the connection from the super triangle is not real, right? For our connection, these points don't exist. We created these points to help us make this mapping. So the next step, what we need to do is basically for any of the triangles that contain the point, the super triangle point, they need to disappear. They need to disappear. So how do we do that? That's simple enough. We're going to come to the top logic of the Delaunay Triangulation logic here. We already have a super triangle here. So I'm going to actually make the super triangle its own variable so I can reuse it and then add it this way. What we can do at the end, after everything is done, we can say, well, go through every triangle in the resulting triangle. The three edges will be AB, right? Which is a new triangle. And then we're going to do BC, which is another triangle. AC, which is a new triangle. I mean, this looks familiar. We've done this earlier above, right? Right here, like this. So basically, that's what we're saying we're going to do here. So I guess I'll name this edge A, B, and C again, just to be consistent. And instead of bed triangle, we're just giving the triangle a name. And now we have three edges that we can use. If any of the points in these edges are shared by the super triangle, we don't want to include it. We don't want to include it in the final triangulation. So we'll say for sanitize triangles. I guess we can make it a dictionary because we want to use the redundancy check. So we'll say string, we'll have a triangle, and then that equals to a dictionary collection. And basically, I mean, we do want to just simply be like, oh, you know what? We're going to get the edge A hash code and then add that as edge A. Edge B is the same thing. Edge C is the same thing. Right? Or I gotta B here. C here. And then we're basically including all of this into a sanitized triangle collection. After we have done all of that, we're going to iterate through the points, super points in the super triangle. And then we're going to create a edge with the super triangle, like so, right? Edge A, edge B, edge C from the super triangle. So we're replacing this with super triangle here. I know this is a little wordy. I mean, this could have been done differently in a more like functional way because, you know, we're doing this quite a lot. You know what? Actually, I think we could do that. Let's do that actually. On the triangle, let's create a function called make or get edges, which will basically generate an array of triangles that only contains 2 of the points. And basically the logic of that will be the copy from our triangulation. This part we'll copy, and then we'll paste under the triangle. Get edges basically is edge A, B, C like so. And then instead of doing this, we do points. Hopefully this is not too difficult to follow. And we have edge A, B, and C. So we're going to return an array of edge A, edge B, and edge C, properly spelled. So get edges will simply give me an array of triangles where each of the triangle will only have 2 points. And basically whenever we're doing that logic in the Delaunay triangulation here, we could go var edges will equal to this, get edge of super triangle here. We can do that. So we don't even have to iterate through the points at all. We'll call this super edges for now. Really bad name, but it's okay. And then this one as well, we can say, for edge in triangle.get edges, we'll just go like this. So much cleaner. And then above here as well, we'll go, hey, for bed triangle, we're going to say var bed edges, or yeah, I guess we'll just call it edges, will equal to bed triangle get edges. And with those edge, what do we do? For edge in edges, we simply replace these edge hash code logic here, like so. And then because we're iterating through all of the edge, we don't have to do edge B, edge C type of thing. And then we can get rid of it like so. Looks good, a lot shorter. Hopefully that wasn't too crazy. Basically, we were cleaning up the edge logic. So this one is array of triangle, super edge in super edges. We go through this sanitized list. Oh, that's not. Hold on. Okay, this is silly. We don't need to do that. We're going to get rid of super triangle here. Okay, the mistake I made was that the way I was going to do it was only going to get rid of the line that belongs to the super triangle. We're trying to get rid of all the lines that include the points in the super triangle. So that actually needs to happen on this step, where before we're adding the edge to the list, we have to go, if any of the points in the edge, right, has the points in the super triangle. So I guess we have to do for loop over for loop, which is a little bit ugly, but you know, it gets the point across. If for point in super triangle, for each one of the points, if the edge contains a point in the super triangle, let's name this properly so we're not confused. If a super point is part of an edge, then we basically don't want to include it. What's the best way to do this? Okay, we're going to do it this way. So first of all, we're going to add the edge to the collection. Once we add it, we're going to check if that edge contains a super point. If it does, because it doesn't matter how many passes, we're going to remove the edge from the list and then break out of it. And we're going to continue. And at the end, we're going to be returning the values, which are the remaining triangles or remaining edges, which is not necessarily a triangle. How do we test this? Well, we can, at the end, emit this only, right? Instead of doing all of these things. We're just simply going to emit this value as a drawing target. And then let's actually get rid of this check so it only draws once. Matter of fact, I'm going to get rid of all the other drawing logic here as well, except the points. All right, commented out the circle. Okay, now I'm going to run this and see the result. And it's already yelling at me. Let's see what the bug is. The bug is that, right. This is assuming that the triangle always have 3 points. We shouldn't assume the number of points. In fact, we can just simply pass the polygon triangle points as a variable. Now, we had to do it the other way because it didn't fully circle around, so it didn't draw the triangle. But we don't need to worry about that because this is just simply a line. So let's see. Hopefully that'll draw properly and not freak out. Great, look at that. So super triangle would have been over here. All the things that belong to the super triangle is now gone. So only the edges are left, right? I can run another one. Boom, another shape. And I can even reduce the count now. You can play around with this a little bit. Yeah, see? And this is Delaunay Triangulation to make neighbor connections. This is the most connections points can have. Also, beautifully enough, I misspelled Delaunay's here. Delaunay Triangulation here. So now we have the triangulation logic. That's one of the things. For room connection, we want to whittle it down, right? So we can actually stay on this triangulation tester because why not? And that whittling down logic is minimum spanning tree. So we have a Delaunay's triangulation already, and that results in edges, which is ironically array of triangles. And then now we have to go through each of the edge and then pick our little path, right? So how do we do that? There are a few ways to do it. The edge itself, if we're navigating the points one at a time, then we have to say, well, these points belong to these points. Like, how do we do that without, reiterating through this all the time, right? Because one way to do it is I can do, point in all the points that we have. We're going to look at every single edge for every one of them. And then if it belongs to the point, then that's the edge we're going to check. So what we can do, I'm going to make a edge mapping for a point. For each of the point, we're going to assign an edge, which would be var point to edges dictionary. Once again, you don't have to do it this way. Alternative way, I actually have implemented this in my own logic in the other direction where I do the edges only. But there's this like handling of grouping that you need to handle, which gets a little tricky. You know what? I'll explain it once, but not implement it so that you guys can do it yourself if you would like to. So you know how like you have, let's say you have some points here and some edges here, right? The minimum spanning tree calculation, by looking at it as a holistic thing, you can do it this way, right? You say, okay, well, we're going to start this one. We include this and we check if these points are already connected. It isn't. So we say, okay, this is connected and this is in group A. And then we look at the next shortest one. Let's say we have something like this, next shortest one. Then we go, oh, here's another one. I'm going to connect them. They have never been connected before. And then we create a new group, B, for example. Now the next line comes to a point where we say, let's check these two. Well, are these points already connected? And they are, right? Because we just connected them. But except this one is connected to A and this one is connected to B. So then the logic is not that connect only the ones that haven't already been connected. It should be connect the lines, allow the lines, if the group that you're trying to connect doesn't belong to each other. So you see that this one is in A and this one is in C or B. So now you're like, oh, they are in two different groups. So we're going to make all of this and all of this a same group. Now this one is called AB or whatever. And that implementation gets a little bit tricky, and it was not fun to implement. Well, it was fun, but it wasn't when you look at the code, when you're trying to follow along what's happening, it's not the most, like, it's not the easiest thing to do. So what I'm going to do instead is I'm going to associate a vector, the point, and that to the edges, like so. Right? Well, I can't nest them, so I'm just going to say this is an array of triangle. Each point might have multiple edges, and if I want to get all the edges that belongs to a single point, I can just get that value, right? So for all the edge in the edges, we're going to go through all the point in the edge. And basically, we're simply going to go over them and say, hey, put the point. Well, actually, we'll have to say var edges for point will be array of vector 2 here, which can be retrieved by doing points to edge, get the key value, which is the point, and then we're going to have a default value, which is an empty array, like so. Hopefully this works. I don't know if it's going to yell at me for the typing issue, but we'll find out. And now this is either a array that already exists or an empty array, right? And basically we're going to say, oh, you know what? We're going to push back this new edge to this thing. And then we're going to add that array back into the dictionary. And we're going to do that for each one of them. And now we're going to have populated list of edges for each of the point, right? And now we're going to have to do some sort of, I suppose, a priority queue. Now, Godot doesn't have a natural priority queue implementation, unfortunately. That does suck. The good news is that I have implemented something called a min heap myself in the past. I don't know if you remember, but there's a video on me creating my own version of A star. And part of A star implementation for path navigation was a need for something called a priority queue, or aka min heap. And min heap is basically a data or graph structure where basically root of the tree is the smallest number always. So it reorganizes a tree as you insert things or take things out so that the next thing that pops out is always the smallest value. So I already implemented this, and unfortunately, I don't think this is in the scope of this tutorial. I'll create a Google Doc with this code inside of it, so you can just copy and paste into your own code to use it if you need to. So at this point, go to the description and click on the link that says min heap, and it's going to be a code in Google Doc. I know. And then you just paste it over, and it should work as is. All right, we're going to go back to our little triangulation tester. Right. We come over here. All right, so first thing we do is we're going to create a min heap. We're trying to navigate through all the points, right? So we're going to make a min heap here, which I guess we could do it this way. And the way to use this min heap is by creating new, and new requires a comparator. And comparator is how this min heap determines the data that goes in here is compared. So A and B, and then you have to return the numeral value for comparing it. Typically you do A minus B type of situation, but since we're saying we're going to put in a vector in here, right? We're probably going to do a distance from these vectors to the target. This is not very clear. I think we do need to do an edge here. Yeah, given the edges that we're observing, we want to pick the shortest edge. Yes. Okay, so this is actually going to be a triangle. And basically, and unfortunately, it's going to be the comparison between A, which is a triangle, points 0, distance 2, A points 1. And then we're comparing those distance to the distance of B edges, like so. And we start by randomly choosing point to explore. So we kind of need a already visited. So let's say we have a vector 2, and then it's Boolean. It doesn't really matter what the value is for now. And this is going to be already visited list. And we're going to say, hey, while the min heap is not empty, visit a point, which will be min heap pop, or yeah. We said min heap is going to include the triangle actually, right? Visiting edge. And then we're going to check the point that we're observing. If visiting edge points, so we got to check both points of the edge. And if one of them haven't been visited yet, then it's okay. Which means the edge is not an option if both of the points are already visited. So we can say, hey, does already visited has this key, point A, and does it have points B? So if it includes both of the points, then we move on. Otherwise, if it hasn't been visited yet, we want to grab all the edges that belong to the new point, the point that hasn't been already visited, right? This also means we have to include a random edge into the min heap. So we'll say the starting edge will be what? What should we insert? We'll just do a random edge. So we'll do pick random, like so. And then none of them will be visited. So basically it's going to go like this and say if point A is not already visited, right? So we're doing this check again. Because either or could be not visited. Then we're going to insert all the edge in this points to edge dictionary. Get point A. It's going to be empty by default if it doesn't already exist, which it shouldn't happen, but it's just something that I'm doing as a guard. And we're going to go through every single edge in this non-visited thing. And then we're going to insert that edge to the min heap. Also, we want to include the points to the already visited list. Yeah, after that we go, whoop, already visited. We're going to assign the vector, this new point here, into this and say true. And we want to do that also for our other point, point number 1, like so. Nice. So this is going to do the check. It's going to continue if both of them are already visited. Otherwise, it's going to add whichever is not already visited. And we're going to grab all the edges that are connected to that point and then recycle. One problem is that when we're doing this, we have a chance of adding back the edges that we've already tested. And so what we have to do, I think, is also have an already visited edge list where we have a key and we don't actually need the edge, I think. And we do something like this. And basically, before adding the edge, if the already visited edge has the edge's hash code, then we don't do it. And we only do this if it doesn't include it. So we add this over here as well at the bottom. Boom. So once again, we're checking for edges. We're inserting it if it doesn't already include. And as we insert them, we have to include them, right? So we go edge hash code will equal to true. The only problem here is that I've misspelled this, so I'm going to Make sure I spell this correctly. Then we're going to do that here as well. After inserting the edge, we're going to get the hash code and say, hey, these edges were already visited. And basically, we want to have a list of selected edge, which will be array of triangles. When are we selecting them, right? We are visiting an edge, and if it is not already connecting things, then we consider this edge selected, right? So visiting edge has been selected. Now, does this work or not is a separate question, so we will have to draw this. So what we're going to do now, instead of relying on the signal, we're simply going to populate this draw triangle at the end of this min heap run. And we're going to say, hey, that is the selected edge. And then we're going to Q redraw, right? And it's going to draw the polyline, right? Because these are all the edges. Let's see what happens. Error. Trying to assign an array of type array to array vector. Ah, right. They don't like these like typing stuff. So I'm going to get rid of that vector too, unfortunately. I have a feeling that might break down somewhere else, but we'll see. Okay. Hey, look at that. That is a minimum spanning tree, right? Where each of the points, there is a single line. This is a minimum amount of line that is required in order to connect all the points within the graph. Beautiful. And I can rerun this to regenerate some different examples, and they kind of look like a constellation. It's kind of pretty. Nice. So this would be one way to connect these rooms. So we did the triangulation to make as many connections as possible, and then we got rid of as much as possible while keeping everything connected. And you have an additional configuration you can do at this point to be like, well, you know what? Out of all the non-selected edges, so let's say we have unselected edge, right? Well, this is kind of a bad way to do this. Let's say, okay, I'm going to change this. So we're going to use the hash code again because we want to fast compare these things. So let's say we have a dictionary of hash code to triangle again. And then for selected edge, we're going to simply, instead of pushing back, we're going to say visiting edge dot hash code will equal to the edge itself. And later over here, we're just getting the values instead. So this will work fine. Now we're going to go through all the available edges again and basically filter them, right? So we're going to say, hey, for the edges, we're going to filter them where the edge is not in selected edge. So this would be all the unselected edges. Has edge. So basically what does it do? Well, I got to do it this way. We're going to make a new list. Camera died again. It's okay. We're almost done here. After this, we'll be done. All right. Well, anyways, so what we're doing is we're getting all the edges that we created in the beginning, and we're filtering by all the selected ones. So this will result in edges that are unselected, right? And then depending on the configuration where we say add back count, which I guess for now I can say I'll add back like 5, might have to be less. We'll just go for I and add back count. Just from the unselected edges, we're going to pick random or pop random. We're going to shuffle. Let's shuffle this first. We're going to shuffle this, and then we're going to pop the back because it's random, right? Once I shuffle it, it's all random. And we're going to pop 1 for each add back count, and then add it back to the selected edge, where we go selected edge, and then we'll probably make sure we do this down here. Sorry if I'm going too fast. Selected edge, pop back will be adding edge, which this one I don't think knows the type, so I don't have to do these typing. Dot hash code will equal to the editing edge, and then we're going to have it. All right, so when we run this, we should be able to see some connections, right? You see new connections that are being made. A little bit of a cycle going on. And you can, of course, increase that count to add back a little more. But now you're starting to get more interesting shape. And that's essentially what you use in order to create this connection thing. And you can probably see how you could use this to randomly generate map and then randomly generate any kind of like one of those Slate Aspire style like map connections where after each round you choose which path to go to, right? Of course, there's easier way to do this if it's like Slate Aspire type. This is definitely more fitting for dungeon navigation as opposed to Slate Aspire type, because Slate Aspire type, requires you to split each option into 2 or 3. So it's easier to draw it as a tree as opposed to doing it as a graph like this. But this is what we get. And this is kind of awesome. Okay, let's increase the size, not the size, but the range of where we are writing this, creating the points. We'll say point is distributed between 100 to 1080 minus 100. We're giving it a little margin. 100 to 1920 minus 100. Right, that's right. This should be 1920. Width 1920, height 1080. Should have been obvious. But yeah, look, pretty awesome. Further along, because I hate relaunching the test in order to newly generate, I'm going to add a quick button here. I'm going to call this generate, and I'll connect that signal, the pressed, into the tester. And basically, when it's being pressed, I want to run whatever's under ready. We'll make a new function called run, like so. And then ready runs 1. And then also, when we are pressing a button, we also run it again. And yeah, this should be good. Let's see. Boom, boom. Oh, yes. Wait a minute. Am I crazy? Is it using the same points over and over again? Hold on. Let me go to the run real quick. Oh, interesting. We got to make sure that the points get reset every time we run a new one, huh? All right, this is no 2D. We have to clear. Okay, so func clear. We'll be making sure that all these children, everything in the points are freed. For point in points, point Q free. So because they need to go away, we'll run clear like so. We run Q free on all of the points, and then we're just gonna empty the array. We gotta make sure that the draw points are also cleared. Like so. Okay. A lot of cleanup that we need to do beforehand. But now we have it. Look. I say that's pretty dope. You know what? For the visualization, I'm going to make those points a little bit bigger. So we'll say the circles for the points will be radius of 5. Beautiful. Look at that. We have a proper map. We can kind of see this looking like a little constellation, doesn't it? Let's see. What does this one look like? This one looks like a person who's about to do an overhead kick. This one looks like, I don't know, a grasshopper maybe? This one is definitely a armadillo. I don't know what this is. But yeah, fun stuff. So yeah, that's the conclusion of tutorial for how to quote unquote connect rooms. But essentially this is how to connect points. And you can use that for any application you need. But mainly we're trying to make it for our dungeon generation. So there is that. Next up, we are planning on doing wave function collapse, I think. That's coming up next. And then some Perlin noise related generation. We still haven't talked about creating corridors for these connections. We have made these like, oh, this is how we would connect the rooms. But is that how you do it? We actually need to draw them out, right? Draw the corridors, the L shape, the reverse L shape, all those things. So we do need to do that. Maybe next time. I don't know. I'll decide on that. Just keep a watch. All right. Thanks for watching. I'll see you next time. Goodbye.